Great. Can everybody hear me? Well, thanks for the glowing introduction, Sonny. I'll try to live up to it. Sonny asked me to just give a kind of a overview of SPICE, where it came from. So I'll try to take you back a few years. The important thing, it was originally released over 40 years ago. So it has definitely withstood the test of time. Virtually, at this point, most of the people in this room probably weren't even born when the first version of SPICE was introduced. I'm okay with that. At this point, virtually every student who studies electrical engineering or almost any kind of engineering has to learn SPICE as one of the prerequisites for getting a degree. That doesn't mean they have to enjoy it, but they do have to learn it. And it's still around basically because it's undergone tremendous evolution in the last 40 years. I'm sure it will continue to evolve over the next 40 years. Just to give you an idea, you know your work is, has gotten there when you end up with a plaque commemorating it. If any of you are lucky enough to visit Berkeley at some time and you have nothing else to do, walk into the electrical engineering building, Corey Hall, and you'll see on the wall a milestone plaque put there by the IEEE, which commemorates the fact that SPICE was written at Corey Hall in 1969 to 1970, making it exactly 40 years old. So that's where it all began. Sort of the motivation behind SPICE. Before SPICE, everything was done pretty much back of the envelope slide rules. We realized that SPICE is just one of many Berkeley CAD tools. I want to emphasize that because it wasn't developed in a vacuum. There were a tremendous number of people working on this problem at Berkeley in the late 60s, early 70s. And what we realized was with having computer tools, students could learn how circuits work much better without having to build them in a laboratory. And so it was really originally designed and implemented as a teaching tool, as something that students could use as part of their undergraduate and graduate education. Of course, as students graduated, they went off and kept their tools. And very quickly we realized that even in the professional world, having computer tools was a very valuable thing, especially because it allowed you to do a complete estimate of how the circuit operated over process, over PVT, process voltage and temperature. Something that you really can't do with a slide rule, and you really can't even do it by building it, because as my research advisor, Don Peterson, used to say, the nice thing about having a computer tool is that every transistor has a beta knob on it where you can turn the beta up and down and see how the circuit works as you vary the beta. So it allows, even then we realized that we were pretty beholden to the sensitivity of the tools, of the elements. The circuit operation had to operate over a wide range, and we had to know what was sensitive and what wasn't sensitive in the circuit. And it also allowed us to evaluate many different design alternatives in an environment where we could get a reasonable estimate of parasitics without building it. Breadboards, even in the 70s, were a little problematic. The disadvantages. And I think, well, first of all, the biggest one, we all know that SPICE doesn't always work. It doesn't always give you the right answer. It doesn't even, maybe not even give you any answer. So there's a certain amount of diddling required. In some people's opinions, and I won't mention any names, but in some people's opinions, it means that the students really spend too much time playing around with computers and not enough time thinking about how circuits work. And I think in some sense that's a valid criticism. Certainly when SPICE ends up on smartphones and people are playing with them on smartphones, the thing that always bothered me is that both students and engineers end up putting entirely too much trust in a computer tool. I've often heard the sentiment, well, of course the circuit works because I put it on SPICE and SPICE said it would work. I wish it were that simple. It's not. So when you want to talk about history, I guess you have to go back to the beginning. And the history of electronics, as we know it, probably started when Lee DeForest invented his Audion tube. Before that, we didn't have any active devices that had gains, so there really wasn't electronics at that. Before Lee DeForest was power transmission systems and batteries connected to light bulbs and whatnot, none of which is terribly interesting. About the time that I came along, the point contact transistor was also invented, and that brought about an entirely new generation of miniaturization with the 5-transistor radio that became very popular in the 50s, that you could carry in your pocket. Before that, nobody had pockets that big. And later in the 50s, the planar integrated circuit process was invented, which, at least in my opinion, was the beginning of the integrated circuit. I realize there's another patent for integrated circuits that doesn't involve planarization. But that was about when integrated circuits became popular. And in 1960, the MOS transistor was invented by Duan Kong at Bell Laboratories. And in '63, along came CMOS down at RCA Laboratories, Sarnoff RCA Laboratories in New Jersey. And really the first of its kind simulation program that I'm aware of was called ECAP. It was written at IBM, Electronic Circuit Analysis Program, and that was in '66. At about the same time, Professor Bill Howard at Berkeley was toying with a daunting problem of trying to get temperature, trying to get band gap regulators to work properly over temperature. And he decided that the best way to tackle this problem was to write a computer program for it. And that program later became called BIAS, and it was, I believe, the first program developed at Berkeley for doing computer-aided design. So a lot happened between 1966 and 1971. There was a team of probably somewhere between half a dozen and a dozen PhD students working on various different tools at that point. I was very privileged to be one of those PhD students. And the tools that came along were called BIAS3, SLIC, and Cancer. I'll do a little more on Cancer later. And then finally, SPICE was released in 1971, and it was very much a team effort. There was a lot of interaction going on to develop these tools. Just to give you some idea of what was going on in 1970, the computer we had was a CDC 6400, Control Data Corporation 6400. It was the sort of the poor stepsister of the CDC 6600, which at the time was the most powerful computer in the world. Because they had one of them at every one of the national laboratories. Lawrence Radiation Laboratory in Berkeley, Lawrence Livermore Laboratory had a CDC 6600, all of which, of course, were used to simulate nuclear reactions. But the 6400 was also a fairly powerful computer. The input to the computer was something which is totally alien to now. Punch cards. You punched your cards on a card punch, and that's how you got input into the computer. And the output was in the form of a line printer, 132 column wide, this wide paper. And the MIPS rate, as near as I can tell, was fairly comparable to an Intel 286, which means that it was 10 times less powerful than what most of you are carrying around in your pocket in the form of either an Android phone or an iPhone, which is mind-boggling when you think about the fact that over 40 years we're now carrying around in our pocket something that was more powerful than the most powerful computer in the world back then. Just gives you some respect for how much the electronics industry in general has accomplished. The maximum available memory back then was 100,000 octal, and if you allow me to call a 60-bit word 8 bytes, which would be 64 bits. 100,000 octals, about 32,000, so that's about 256 kilobytes. Not an awful lot of memory. Every one of those cells of memory was precious and had to be reused and watched very carefully. And now we're carrying around 4 gigabytes in our pocket, or 16 gigabytes, or however many gigabytes you happen to have in your pocket. So by any estimation compared to this today, the computing resources were crude. A little better than the mechanical calculators that came before, but not much. So back in 1970, probably the benchmark circuit that everybody wanted to be able to simulate was the Fairchild UA741 op-amp, which at the time was the state-of-the-art integrated circuit. And because an op-amp had to do so many different things, there were a tremendous number of characteristics of the op-amp that we needed to explore, needed to understand as part of the design. We needed to know how well the DC operating point performed, especially how sensitive it was to process variations. We needed to know the small signal characteristics, the AC small signal characteristics. We needed to know slew rates, so we needed to be able to do transient analysis. We needed to know noise, in fact, and we needed to know distortion, and there were numerous other analyses as well. So this is the famous 741. By today's standards, this isn't a very large circuit, but most simulation programs in the 1960s, this was too large a circuit to be able to simulate at one time. It had to be cut into parts, and the boxes show the various parts it had to be cut into. So the program basically started as a class project in the school year 1969 to 1970. At the time, Ernie Koo, who was a very dyed-in-the-wool circuit theory guy, had a series of courses on circuit synthesis, which was how you would generate, given the fact that you want a particular frequency response, how would you synthesize a circuit to give you that response. Something that I don't think it's taught today in schools, but it was taught back then. Ernie took a sabbatical, and Ron Rohr, who had just showed up at Berkeley, was given the job of teaching Ernie's classes. And much to Ernie's horror, Ron said, well, nobody needs this circuit synthesis stuff. I'm not going to teach that. I'm going to teach a class on circuit simulation instead. And immediately, 2 of the 12 people in the class walked out in shock because they didn't even know what circuit simulation was, and they didn't want to have anything to do with computers. They were dyed-in-the-wool circuit theory guys. The rest of us said, well, okay, what is, what is. And The ground rule was that Don Peterson would be our judge, and if Don Peterson liked the program we developed, we'd all get an A, and if Don Peterson didn't like the program we developed, we weren't going to pass the class. So it's pretty clear-cut set of criteria, and because I had worked as an undergraduate on an undergraduate project with Don Peterson building an integrated circuit, they said, look, you know Don Peterson, you can be our liaison, make sure that Don Peterson likes this program because we really do need to pass this class. So over the course of the next 3 quarters, we developed a program called Cancer, and it was after the class, it became my master's project to sort of finish it off. It was capable of analyzing a 741 op-amp, which was basically the overall goal that we'd set for ourselves. Could do DC operating point, small signal AC, and transient in one package. Now, recall before then, you'd have one deck of cards that you ran on your DC bias program. You'd then translate that deck of cards into another deck of cards with a small signal circuit that you could run on a program called SLIC and get the AC response, and yet a third deck of cards which you would run on a transient analysis program. Now imagine the probability of having all 3 of those decks of cards describing exactly the same circuit. It's pretty close to 0. The beautiful part of this program was that you only needed one deck of cards. You made a change once. It was shown immediately in your slew rate, your small signal, and your DC operating point. Nowadays, you say everybody's used to that, but believe me, this was a big thing. It also, like all the other Berkeley programs, had built-in models for the devices. ECAP, on the other hand, and other early circuit analysis programs, your device model, you wrote your own Fortran program, which you linked into the main program. So having built-in models, especially for students, was a tremendous boon. And to my knowledge, this was the first program that utilized sparse matrix techniques, and that's what allowed us to analyze a circuit as big as a 741 op-amp. Prior to that, 10 nodes and 5 or 6 transistors was about the limit. After that, you ran into serious problems with the matrix package, just because you were analyzing a full matrix and it's an n-cubed process. And as I said, this thing wasn't even as powerful as your smartphone. So you ran out of gas pretty quickly. It also used a modified Newton-Raphson iteration. At that point, MOSFETs really hadn't been introduced to the mix, so we were entirely a bipolar house. And the heuristics that we developed worked very well with bipolar circuits, the old 2BT, 10BT convergence criteria. We used implicit integration, which allowed us to deal with the large time constants that are in 741 op-amp, for example, has hundreds of megahertz time constants, and you're usually slewing the thing over so many volts per microsecond, if you're lucky, something around there. So there's many orders of difference time constant in a typical op-amp or any other typical circuit. And we also use the adjoint network concept developed by Steve Director and Ron Rohrer, which allowed us to very rapidly evaluate sensitivity analysis, noise analysis, and distortion analysis. Prior to that, it was an n-cubed process. We reduced it to an n process. And it wasn't a very big program. It used about 6,000 lines of Fortran code. The Cancer never was released. At that point, Ron Moore elected to leave Berkeley and go work in the public sector, the commercial sector. And I finished my master's program, and Don sort of adopted me as a PhD student. And my first job was to come up with a new name for cancer, because it had some it had some unintended side effects, as you might imagine, with the people that had loved ones who had cancer. This wasn't a very popular name. So we came up with a better name. Cancer, by the way, I should have mentioned, was, I need to attribute that to my first wife. She came in to pick me up after a day of work, and I was sitting there puffing away on my pipe with 3 or 4 people huddled around, and we were trying to come up with a name for it. And she said, well, why don't you call it cancer, because that's what it's giving you. And I puffed a couple more times on the pipe. It said cancer. Well, computer analysis, of networks, computer-aided analysis, nonlinear circuits, and then we said excluding radiation, because all the other programs that were being developed were funded by the government. At this point, we were worried about nuclear weapons, their nuclear weapons, disabling our nuclear weapons so that our nuclear weapons wouldn't be able to destroy their nuclear weapons, which were just trying to destroy our nuclear weapons. There was a lot of money in radiation analysis, so excluding radiation was sort of the Berkeley statement. Hey, we did this on our own. We don't need the Department of Defense, and we're not going to do radiation analysis. And it was a very nice, bold move, but turned out SPICE was a much more likable name. The other major thing that happened was that Dave Hodges came back from Bell Labs, became a professor at Berkeley, and he'd been doing a lot of work on MOS memories, MOS digital logic, and he pretty much introduced the MOSFET into the Berkeley curriculum. And this was a good time to do it, because everything was going MOSFETs. So SPICE became a simulation program that could also handle MOSFETs. And as I said, at this point, undergraduate students used it because they had to. Graduate students used it because they realized it could really make their research a lot easier. It was a public domain program from the very beginning. So students could walk away with it, take a copy to the company of their choice when they went off to work. It had all of these analysis capabilities. It had, at this point, built-in models both for bipolar transistors and for MOSFETs and JFETs. And the fact that so many students knew how to had to use it meant that a lot of my time, a lot of my fellow graduate students' time was devoted to making it very bulletproof, because the last thing in the world you wanted was to make a change to the program the day before or the night before the final project was due, and kill everybody's simulation and have 15 or 20 or 30 graduate students in your office at 2 o'clock in the morning screaming at you because their simulation didn't work. So it forced us to make the program very bulletproof. And as I said, it was written in fairly portable Fortran, so there became versions that ran on just about every computer that had a Fortran compiler. The limitations, it was certainly, nobody considered it to be a very user-friendly program, although we didn't use that term back then, but it wasn't user-friendly. If you didn't do it the way that it had been designed to be done, it didn't work right. There was a limited amount of error checking. It required a fair amount of intelligence to run it. And there was large problems with convergence, still famous for that, and had no time step control. There was no dynamic memory allocation, so one size had to fit all. And so that meant that the program had to be run very late at night when when they could drop a piece of the operating system and give us some additional memory. And after all, this was a class project. This wasn't something that this wasn't a 30 or 40 or 50 staff year project funded by IBM to the tune of millions of dollars. So you would expect that there'd be a fair number of warts. Enough warts that I was able to get a PhD out of it. SPICE2 became my PhD dissertation. And I ended up totally rewriting the program, redoing the algorithms, and in my estimation, at least, making it a good deal more usable. That version was released in 1975, and it was upward compatible with the original version of SPICE, but the data structures, if you can even imagine taking of the Fortran language and doing dynamic memory allocation. It's a fairly easy thing to do in C and any of the modern programs, modern languages that have come after C. It was not a fairly easy thing to do in Fortran. I'll let you take my word for that. But in addition to the dynamic memory allocation, which meant that now we could run it during the day, students could run over and get their results back in 10 or 15 minutes instead of having to submit their deck, have a TA take it over at midnight, run it, and they would get their results the next day. And as a result of all of this, I'd added an extra 2,000 lines of code. So I took 6,000 lines, rewrote it about 4 or 5 times, which means that 30,000 lines of code got written and boiled down into 8,000 lines of code. I know these are minuscule numbers by today's standards, and I'll get to that shortly. I finally ended up taking a job at Bell Labs and leaving Berkeley. My wife never thought I would. And I sort of gave the reins over to Ellis Cohen, who was my office mate. And he spent a tremendous amount of time actually getting it to work right, because after all, I was really more a circuit designer than a computer programmer. Ellis was definitely the computer science guy on the floor. And Ellis eventually also had to graduate, which meant it got passed on to Andrei Vladimirescu, who is still a professor at Berkeley, at least half-time. And he's the guy who actually ended up making the program SPICE2G6, which is now sort of considered the gold standard. If you have a program that you want to claim as SPICE compatible, it better be able to take a SPICE2G6 and run it and give you the same answers that SPICE2G6 would give you. So that's sort of the standard that everybody has had to adhere to. And that program, again, that was 1981. So now we're fast forward another 6 years of development time. SPICE2 was, again, as people graduated, they took it with them. And so it replaced SPICE at most of the universities. And it actually, the very first issue of the book by Paul Gray and Bob Meyer, which is, at least in Berkeley, is considered the analog Bible. I know if you go to other schools, it may not have quite that distinction, but it's a known book. And it was the first book that actually the problems had said, use SPICE to demonstrate that the temperature dependence of this circuit is far superior to the temperature dependence of the circuit in Figure 2. Use SPICE to do this, run a SPICE run to do that. So at this point, this was engraved in students' minds. There was no way of getting a degree in electrical engineering and not owning up to the fact that you had to use SPICE. Maybe in very special cases you could avoid it, but I don't know of too many of them. And SPICE2 was also a platform for many, many master's projects. Many people put various different enhancements or use SPICEs one way or the other. And in addition, it crept into the commercial world. There were several, at that point, proprietary versions. I obviously took a copy with me, and it turned it into a program called Advice at Bell Labs, which actually was still at Bell Labs when Bell Labs disintegrated. So it lasted as long as Bell Labs did. Texas Instruments had a version of SPICE called TI SPICE, which just recently, I think, was replaced by something called Mica. Or no, that's Motorola, I'm sorry. Maybe it's still called TI SPICE. And Motorola's program, MC SPICE, started Motorola and then later became called Mica. In addition, a couple of enterprising brothers who worked at AMD came up to Berkeley and checked out a copy of SPICE2E and took it back and turned it into a program called HSPICE, which became probably the most successful commercial version of SPICE. Successful in the sense of if you count dollars. I'll get to the other successful version of SPICE in a minute. And there were numerous other alphabet SPICEs that were around, still are around. I guess as a tribute to Don Peterson, everybody kept the name SPICE in the title somehow. So there was an A SPICE all the way to a Z SPICE, and then there were SPICEs with 2 letters in front of them, and it kept going. So again, the theme that comes up over and over again, the biggest reason it was a success was that it was in the public domain and it was free. So A, you didn't have to spend a lot of money for it. B, if you wanted to fix it or add something on your own, all you had to do was program it. You had access to the source code. And at this point, I guess by this time in the timeline, people were actually starting to talk about open source programs. Unix was becoming popular. People loved the idea of here's an operating system that I can actually go in and fix the operating system instead of filing out a trouble report in triplicate, giving it to IBM, having a committee decide which committee should go over to the committee and decide which enhancement would go in. And you'd never get your enhancement done. So public domain was a very powerful mover. People knew the code, people had access to the code, people made improvements to the code and made those improvements popular. And in some sense, that gives SPICE the bragging rights to be one of the very first open source programs. Long before the term open source had been coined, SPICE was public domain, it was open source, and it was well supported by many sort of nonprofit organizations, if you will. It was totally compatible with the original version of SPICE, which I found out later in life. Upward compatibility is the only way to survive in the world if you're a software developer. Had dynamic memory allocation and vastly improved convergence and transient time step control. And it also had many useful features such as subcircuits and transmission lines and whatnot. So then once SPICE2G6 hit, at about the same time SPICE2G6 was being developed, Tom Quarles took a version of SPICE and recoded it first in RAT4 and then in C and called it SPICE3. And it had roughly pretty much the same capabilities as SPICE2, but it was completely recoded in a more modern, more flexible language. And one of the prices that had to be paid for this was that the code went from 8,000 lines of Fortran to 135,000 lines of C. Something I still, to this day, I've recompiled. To me, this is mind-boggling. But it's obvious that somewhere along this line, you stopped having to carry around cards, and you started having everything stored on disk space. because nobody can carry around 135,000 lines of cards. And maybe we should have just kept the card reader, and then all of our programs nowadays would be 10 or 12,000 lines of code. We wouldn't have these million-line monstrosities. But nonetheless, so it blossomed into 135,000 lines of code. It was presumably much easier to support, and definitely much easier to add models to. And that latest version was released in 1993. You can still get it from the Berkeley website, but there's basically hasn't been any work at Berkeley done on SPICE since 1993. So SPICE3 was an incredible success among the Unix, C, computer science types who like to embed SPICE in a much larger version of some computer-aided design project. It was very flexible, and it could run on anything that had a C compiler, which back in the 1990s meant just about anything. And so there's a lot of new research that came about that used SPICE as a very as the lowest level piece of the program. Commercially, the largest commercial success was PSpice. The Microsim picked up a copy of the program and turned it into what is arguably the most successful program if you count number of copies distributed, and that's because they gave away the student version and charged for a more complete version. But that's a very convenient way when you don't have an open source program. If you want to get students hooked on it, you give it to the students for free, and then when they go out to their company, they say, "Oh, I got to have this program," and very successful. A strategy that has later been adopted by Cadence, Synopsys, Mentor Graphics. They all give you a limited version in hopes that you'll buy a complete suite of the program when you're in a position to do that. So as I say, SPICE3 was successful because it was more elegant, it was written in a modern language, and it was much easier to embed in Unix-based systems. So right now I've covered through, starting with SPICE1 in 1973 up to SPICE3. There were several other commercial programs definitely worth noting, in addition to HSpice and PSpice. About the same time that PSpice came out, a program was started under the auspices of the French government by a grant called ELDO, which was sort of later became the European version of SPICE. And then ELDO was purchased. The company was purchased by Mentor Graphics. So the European version of SPICE is now owned by Mentor Graphics, whose corporate headquarters are in Oregon. So go figure. Spectre was written at Cadence by Ken Kuntert a few years later, and this was Ken's way of rewriting SPICE in a way that he thought was more useful. And as I say, SPICE3 was started in 1989. It was finally released. The last version was released in 1993. And that's sort of the end of the line in terms of SPICE development at Berkeley. And during that period, what had happened? Well, the SPICE applications were still, by today's standards at least, mainly analog circuits, which were relatively small, maybe 100 transistors, maybe 1,000 transistors. They were critical paths in digital circuits, and because it was just the critical path, that wasn't a very large circuit. And there were critical portions of memory circuits. SPICE was exhaustively used in designing memories because dynamic RAMs, static RAMs, both had extremely tight operating conditions over process voltage and temperature. and an enormous amount of computer-aided design time went into designing memories. So this, as a result, the SPICE algorithms were sort of tuned to be faster, but didn't really work much smarter. They just did things faster. And there were a lot of things that came up, like switch capacitor circuits, for example, which you just couldn't analyze with SPICE properly because of the time constant problem. They're such widely spaced time constants, and they actually developed special purpose simulators. So you saw a lot of special purpose SPICE-like programs come up, like SWITCAP, that was developed at Columbia under the auspices of Janis Savvidis by Mike Fang. So again, the 741 is a classic example of the small analog type circuit that SPICE was used for. Something like this is a worst case Domino Logic path that was actually today, by many people's estimation, I think it's correct, most of the SPICE CPU time today is spent doing cell characterization, analyzing digital cells to derive models which can then be used in these monster timing simulation programs and logic simulation programs. But this was also not a tremendously large, challenging project. And then, of course, there's the DRAM. DRAMs are huge. There's millions of transistors. But typically, all one needs is the logic for the row decoder, the worst case path of the row decoder at least, one row of memory, and perhaps two of the nearest neighbor rows on top and bottom of that row, and one particular column, probably with two columns, one column on either side. And the sense amplifier circuitry and the worst case column decoder circuitry, and that pretty much gets you the access time of the memory. So you can get a lot of information out of looking at a very small subset of the DRAM itself. And basically, everybody needs to mention Moore's Law when they give a talk, or it's not an official talk on an integrated circuit. So I just thought in a kind of a Fortran-like way, if you look at the CPU you spend on SPICE, it's a function of the time points times how many Newton iterations you spend on a time point times how much CPU is expended per Newton iteration per transistor times the number of transistors. And if we break this down, because the worst case path is getting longer and longer as time goes by, or the circuits are getting bigger, the number of time points that you have to go goes somewhat as the number of transistors, which is basically, according to Moore's Law, square root of 2 every 2 years. It increases. The number of Newton iterations you spend per time constant is pretty much, per time point, is pretty much a constant. So it's 3, okay? Maybe it's 2, maybe it's 4, but pretty much it's 3. No changes there. The CPU per Newton iteration per transistor is pretty much, that's how much time is required to evaluate a transistor model. And that's pretty much a function, that's pretty much constant over time. The model equations stay the same, or don't stay the same, but the complexity of the model equations doesn't change by that much. And the number of transistors that are in the circuit increases by about a square root of 2 every 2 years. So if you run through all of these things, you see this is at least an n-squared process. The number of computers that you have to buy per year goes as n-squared, which is great news if you work for IBM or for DEC. Maybe not so great news if you're a circuit designer and you keep running out of computer time. So fortunately, the thing that saved our bacon was that SPICE is being used to design all these new computer circuits, and the computers are going roughly a square root of 2 faster every year. So, nonetheless, every 4 years, the SPICE CPU consumption doubles, which is interesting. And in fact, when we added a 5th floor to Corey Hall, there was a big fundraiser to raise the money, and they went to Digital Equipment Corporation, and Digital Equipment Corporation very gladly chipped in a very large check. And they said, look, we have no qualms about this. We figure that there's at least 1,000 VAXs doing nothing but running SPICE. 1,000 VAXs. And at that time, a VAX cost about between $250,000 and $500,000. So do the arithmetic. Writing a check for a couple $1 million for a new floor on Corey Hall was the same as erasers and paper clips, right? So, and I'm sure IBM was thrilled to see this newfound CPU burner. So SPICE certainly has become known as a tool that keeps computers busy. And just to end the talk, this isn't really part of the SPICE story, because the SPICE story, at least at Berkeley, sort of ends with the final release of SPICE3. But that's certainly not the end of the story of SPICE in general. And the next most important thing that happened was the fact that was good old Moore's law, kept making transistors smaller and smaller and smaller. As a result, the FTs of the transistors got larger and larger and larger. And finally, these things that could barely get out of their way at, remember that the very first microprocessors ran at a blinding speed of 5 megahertz. And now we're talking about clock rates in the gigahertz range. And somebody, I'm not sure who it was, came up with the brilliant idea that, you know, we could actually make a radio with CMOS. And that was what started what I call the RF revolution. It did require an entirely new line of algorithms. And rather than incorporate the algorithms into SPICE, it actually sort of put a fork in the process, and it got a brand new set of programs that weren't really SPICE, but they really were SPICE. And I'll explain a little more. So this became the new UA 741, the RF Transceiver. And it became necessary to simulate in one fell swoop everything starting down here with the low noise amplifier and the mixer and some kind of frequency synthesizer. And that mixed the program down to baseband, which then went out to your digital signal processor, which did all of the work that was required. Coming back in on the transmit side from the digital, from the DSP through a programmable gain modulator and frequency synthesizer, and out the power amplifier driver, and finally to the transmitter path. The real dream of getting everything on the same chip kind of got, it was very difficult to put the power amplifier, which dissipates on the order of almost a watt of power, on the same chip as all this other stuff. So the best we could do was a power amplifier driver, and then off chip to a power amplifier, which was a separate heat-sinked, moved away project. So this sort of started in 1988 when Hewlett-Packard developed a program called MDS, or Microwave Design System, That evolved, and that sort of led to the evolution of a program called Libra by a company called EE-Soft down in Southern California. Hewlett-Packard then became Agilent. Agilent purchased Libra, mixed it together with MDS, and that's where ADS came from, and that's one of the now thoroughly acknowledged RF programs. Spectre RF became the RF algorithms were added to Spectre to make it an RF analysis program, and in short order, Eldo had an RF package, HSPICE had an RF package, and a new public domain program evolved called QUAC, Q-U-A-C, which is Quite Universal Circuit Simulator. If you look at all of these programs, only one of them is public domain, and that's QUAC. So all of the RF stuff became proprietary, and unfortunately, every simulator had a slightly different personality, and not only required a different amount of runtime and worked better on some circuits than others, but you had a hard time, if you tried to benchmark these things, you had a very hard time getting the same answer out of all of the simulators, which led to a certain, there's a nice thing about having, that's the open source commonality there. You like to get the same answer out of all of the simulators you're using. It gives you a good warm feeling. And not only that, but the user interface varied, the netlist description varied, and for RF designers to have to deal now with 2 or 3 or 4 different programs, it was right back to the good old Berkeley days of 1966 when we had 3 or 4 different decks of cards. We didn't have decks of cards anymore. We had different files, different data files, but it was the same problem. They all gave the same different answer, and a lot of times they didn't even describe the same circuit. And it also, because it wasn't open source, RF simulators are still working very hard trying to work their way into the curriculum at various universities. So to summarize, I've sort of started with the evolution of SPICE. In the beginning, the dream was that if we could run a circuit as big as the UA741 op-amp and do all these different kinds of analysis, that was where we all wanted to be. And we got there first with cancer and then with SPICE. It almost as soon as DRAMS became important products, SPICE became an important DRAM analysis tool. So that was sort of the next big addition. And as digital circuits became more and more important, after all, a digital circuit is just an analog circuit, which usually is overdriven. So SPICE is beautiful at digital circuits, and it became a huge component of SPICE, running digital cells. And then finally, the RF revolution came in, and at least SPICE-like programs entered the scene to do sinusoidal steady-state analysis for RF design. So the question, why is SPICE still around after 40 years? It's the only program I know of that is still here 40 years later, pretty much in its same state that it was. I guess you could make the argument that spreadsheets, it's pretty much the same program, but there's been a lot of evolution there. It's a very handy, useful tool that can accurately simulate most of the necessary characteristics of analog circuits. And it's in the public domain. You can download it for free. Everybody learns it as part of their curriculum, so it's a well-known product, and it's clearly the industry standard. But there's more of a reason, I think, that I'd like to pay tribute to, and that was there were two visionaries in the integrated circuit industry. The guy who actually started this program was Ron Rohr, my master's advisor and very good friend, and Don Peterson, who was my PhD advisor and my very good friend. And there was also a tremendous amount of effort on the part of a huge team of graduate students at Berkeley and then later throughout academia who made contributions to SPICE to make it what it is. So with that, I'm reached the end of my slides and I've reached the end of my time. So thank you very much.